All right, we started with your linear maps 2 days ago. We keep going in this direction. If you knew, today we're going to discuss some concepts attached to linear maps. The first one I'd like to discuss with you, it's called kernel space or null space of a linear map. Basically, we were going to discuss a few new terms, a few constructions which are linked to linear maps. In principle, this is a relatively easy subject. It's just new terms, new ideas which you need to remember. So these are two identical terms which represent the same object, kernel space, or simply kernel, or null space, and there's no any simple version of the null space. What it is this. So we start with the linear map between two vector spaces. We just, we always write, if you would like to specify the operations, and if you would like to specify the scalars we use for the vector spaces, we write it like this. So we have linear map. These are vector spaces. The null space, which is associated with the linear map. These are the notations we often use. Two different notations. They use equally often in books, in textbooks, including the yellow book. Kernel of a linear map or null space of a linear map. These are just the notations. The actual definition, it is like this. This is a collection of all those vectors in the domain. This is a collection of all those vectors in the domain which are sent to zero vector by your linear map. That explains the term the null space. It doesn't explain the term the kernel. Historically, this is also called kernel. That's why we do that. The main thing, I still need your attention. Thank you very much. The main thing which you need to know about the null space is that the null space actually a subspace of the domain. Okay, so in the subspace, in the full meaning of this term, as you know from the chapter 2 in our discussions. So this is something which I call lemma. The null space, which is a subset in the domain, it's a subspace in the way we know subspaces. It's a good opportunity for us to test, to use our skills again, the way we prove subspaces, and I will use this opportunity. So here's the proof. The proof is standard, but well, you live through this topic long enough to accept it is a standard proof. We need to test three requirements of a subspace in full accordance with the subspace theorem or subspace lemma, whichever way you like to call it. So we need to test three things in relation to this. So first thing we test is that the zero vector belongs to this null space, to this proposed subspace. And that's how we test it. We just make the observation that if I apply T, a linear map to a zero vector, we discovered this 2 days ago, the result will be zero vector. That's why zero vector here satisfies this relation. That's why zero vector belongs to the null space. The first requirement of a subspace lemma or subspace theorem is checked. Second requirement, it says this: if I start off with two elements of my null space, I need to convince everyone that if I add them up, the result will be in the null space. So here's my argument which tries to convince you. So first I interpret what it means to be in a null space. This is the interpretation. What it means to be in a null space is the interpretation. It means that T of x is 0 and T of y is 0 combined. This is my interpretation of two elements being in a null space. Now, I will employ some properties of the linear maps we know from 2 days ago. I know that the linear map of a sum is a sum of individual applications of the linear map to the terms, x and y. Each of them individually zero vector. This is my interpretation from here. And that's why the sum is 0. And hence, for the new vector, for the vector x plus y, this condition is also satisfied. Hence my conclusion that x plus y is also the element of the null space. Second requirement of the subspace theorem is verified. Again, as before, I made this point a few times, every time you prove something, you borrow something from the past. There's some piece of the information or piece of the knowledge or result which you use from the past. In this case, is this result, this step, where we use the properties, property A of a linear map. The last thing which you need to check, which is a part of a subspace theorem, is that if I take an element in my null space, I need to show that if I scale this element with any possible scalar, the result will also be in the null space. Again, first I interpret what it means to be in a null space. This is the interpretation. I just copied it here. T of x is 0. Now, if I want to see that the scalar, scaling vector, let's say lambda x, if I choose a scalar, say, if I choose a scalar, if I want to see that lambda x is a null space, I have to test for this vector the same condition. And here's my testing. If I apply my t to the lambda x, again, I borrow something from our baggage of knowledge. I borrow the fact that scalar can be taken out of a linear map. This is the fact I borrow from 2 days ago discussion. And because this is a 0 vector, right in here, you scale the 0 vector with no matter which scalar, result will be 0 vector all the time. And that is exactly the verification of this condition for the new vector, for the vector lambda x. And that is true for any scalar in my field F of scalars. Remember, F is always, it's a cumulative term which can cover either rationals, reals, or complex numbers. And this is the end of it. So the null space, that's the one which we define like this. It's something which is attached to a linear map. It is true subspace. We just verified that. Okay, if you remember our discussions of subspaces, I was trying to make this very clear from the very beginning that all of the subspaces you see, they split in 2 different categories. One of them I call the orthogonal complement subspaces. The other one I call the span subspaces. And every time we met a subspace or we prove something a subspace, I try to always to keep these categories clear and position this particular example into one category or into the other categories. Right now, we're just meeting new subspaces which are linked to linear maps. Soon, you will realize that these two, they actually also part of one of those 2 categories. In fact, the null space, it will be the alternative approach to the first category, the category which we call the orthogonal complement subspaces. And that's the content of my next slide, actually. The slide itself is called examples of null spaces, but when we finish this slide, you will realize that actually null spaces, this is another way of looking at the orthogonal complement subspaces. So actually null spaces is the whole first category of the subspaces we met before. Or I can say it like this: any orthogonal complement subspace you met before can be looked at as if it is a null space of some linear map. All you need to do, you need to make an effort and identify this linear map. And I'll show you how to do it right now. Look at this. So it's the first example of a null space on the slide, orthogonal complement subspace. So in general, remember, it was something like this. I use this symbol, S sub R A. It was S sub C as well. It's the same argument works for that version as well. That's the symbol which I used to denote those subspaces. That's the definition I gave you the very first time we started discussing this category of subspaces. It's the collection of all n tuples, which is subject to relation like this. And that's relation, you can think of it as a dot product between n tuple A and n tuple x. So this x with indices, it's my regular convention. When I speak of an n tuple, say A, the elements of that n tuple, I use the same letter but with indices to denote the elements of that. So is my regular convention. The x vector is supposed, we assume it consists of the x sub k components. A vector, we assume it consists of the a sub k components. It's a regular convention I will follow all the time. Right, so this is the orthogonal complement subspace, the way I introduced it. Now I will make an effort and I'll show you that you can look at the same subspace as a null space of some specially chosen linear map. Here's my choice for a linear map. Look at this. I'm going to choose a map which takes n tuples into real numbers. So you see, I make a clear identification. What's the domain of my linear map? What's the codomain of my linear map? And that's the formula for the linear map. It will take n tuple into the dot product of that n tuple with this fixed chosen vector A. So for any n tuple in Rn. This is a linear map. You can check it directly. I mean, you can try to check, you can check this little a and little b properties of a linear map from 2 days ago. Given that A is fixed, you can just use the properties of a dot product, or I can do it even in a smarter way, convincing that this is a linear map. I can say something like this. I can say this dot product, I can think of a dot product as a matrix product, as a matter of fact, isn't it? If I take a matrix capital A, which is one row matrix, n column matrix, and which consists of the elements of my A as columns. So basically I just transposed my A. Or normally when we think of a vector, we think of a column vector, isn't it? So if I transpose it, it becomes a row vector, or it's a matrix of one row and n columns. If I just introduce this auxiliary matrix, capital A, then my T, which I define like this, equally I can write it like this. It will be a product of this special matrix A with the n tuple or column vector X. And now I can just refer to the fact we just discussed with you 2 days ago. 2 days ago, we introduced these matrix type linear maps, which are constructed by multiplying a fixed matrix by vectors. That's a special case of that kind of maps. And for those maps, we have proved that they are linear. That's why this one is also linear. So that's a good way to prove it. If you don't like it, you can try to attempt it directly. In fact, I encourage you to attempt this directly to show that this choice of a map is a linear without making reference to the matrix type constructions from 2 days ago. It's a good practice. You can try it. But for my purposes, what I'm actually looking at, for the purposes of this slide, if you're now convinced that this T is a linear map, all I can say now is that the orthogonal complement subspace, which is this one, isn't it? It is exactly the null space. It is exactly the null space of this specially chosen linear map T. Because the null space of this T, it's all those vectors which are sent to zero vector, which in my context, zero vector is just a zero number. And this slide and the previous slide today gives you alternative proof that the orthogonal complement subspaces, they are true subspaces. Not directly, as we did first time we met the subspaces, but now through the null spaces. So, as I promised, you see null spaces by themselves cover the whole first category of the subspaces we studied before, those which I used to call orthogonal complement subspaces. They cover even more, in fact. Remember, I split my subspaces in 2.5 categories. There was a little half there. The half was going for this intersection thing. It was a lemma of intersection of subspaces, if you remember, which said if you intersect two subspaces, the result will be another subspace. Well, null spaces will cover for this half as well. Look at this. Here's a typical example. It's the second example on this slide. Imagine I have a subspace which is intersection of two orthogonal subspaces. You see, S R of A and S R. So I fix another vector, say B. I gave a name B to that vector. I took the intersection. We know from our previous experience the result will be a subspace because every individual orthogonal complement subspace is a subspace. When you take the intersection, it will be another subspace. In the explicit form, it's something like this. It's all the n tuples, where these two identities are held simultaneously. Sorry. We know from the past experience this is a subspace. But what I'm about to do, I'll show you that this construction as a whole, it is also a null space of some properly chosen linear map. And that's my choice. Let's just assume that my B, again, that's a regular convention, that the elements of my B vector, I'm going to call them B sub k. if I take this matrix, if I take a map, look at this, a map which takes n tuples into couples, and that will be again a matrix type map, but this time my A matrix will have these components. Look at this. This time my A matrix will have the first row filled with the components of A vector and second row filled with the components of B vector. If I take such a matrix, I claim that the null space for such linear map will be exactly this S in here. And that's not really a big claim, isn't it? Because the null space is when you send, when your vector is sent to 0. If you put here, if you multiply this matrix by the n tuple x and equate it to 0, it will be two equations. One of them will be this equation, and the second one will be this equation. So null spaces, it's even more effective way of looking at this first and a half category of subspaces we knew from 2 or 3 weeks ago. And it's very good, very effective. It's a new way which I encourage you to use to look at those subspaces. Any questions? Okay, we still have the whole category of subspaces. And this second, so remember, we had 2.5 categories: orthogonal complement subspaces and intersections, which are now fully covered by null spaces. There was a second category, which I called span subspaces. On my next slide, I'll show you that the span subspaces, they also can be linked to linear maps. But for that, I'll need a new concept attached to linear map. Look at this. It's called range or image of linear map. Two different names. They denote the same concept. I'll start off again with the same setting. I have two vector spaces with the same set of scalars, vector spaces. I have a map, linear map. So we know what's a null space for this setting. The image or the range of this linear map, that's the definition, that's the notation, IMT. We often use IM letters to stand for the imaginary part of a complex number. It's the same notation, but given that the complex numbers never mix up with the linear maps, you can't really mix them up. I mean, depending on the context, the abbreviation IM, you will interpret either as an imaginary part of a complex number or image of some linear map, depending on the context, and you have to judge the context, of course. So the definition itself is this. It's a collection of all vectors in the codomain this time. Remember, the null was here, the null space was in the domain. The image is actually in the codomain, in a W. It's a collection of all those vectors in the domain, which can be reproduced as the image, as the name explains, as the image of some vector in the under the map T. That's a longer version to write. This is a shorter version to write the same thing. All of the images of X vectors when X freely runs across the domain. This type of subspaces, they will cover for the second category, for the span subspaces. I'll show you this on my next slide, but before I do that, I need to show you again, it's another opportunity for us to practice the subspace theorem. I need to show you that this image is true subspace, so it is subject to subspace theorem. Here's my demo. The image, which is a subset of the codomain, it is a subspace. It's another opportunity, like I said, to try our skills in using subspace theorem. I had some reports from some of the tutors who said that not everyone here is comfortable with the subspace theorem, judging by the test results. So here's your another proof by subspace theorem. So we need to test three conditions of subspace theorem. First, I need to show that the zero vector is in the image. All I need to do to convince that the zero is in the image is to write up this. Zero vector is the image of a zero vector. So there is an element in here, zero vector, which returns zero on the right-hand side. And that's why zero vector is in the image. Second one is the one for the sum. So I need to take two elements in my image. This time I use the letters y1 and y2 rather than x and y. And I think the argument I'm about to show it will explain why exactly this is a better choice for notations this time. y1 and y2 from the image. Being in the image, I start interpreting that. Being in the image, it means that these vectors can be reproduced as the result of t. So being in the image, it means that there are elements in the domain, x1, x2, such that y1 is the image of x1, y2 is the image of x2 combined. This is just the interpretation of being in the image. Now I need to see why the sum of y1 and y2 is in the image. For that, I'll just make a substitution. I use the right-hand side here. And again, I borrow something from the past. That's the place where I just borrow it. Here it is. I know that because my map is linear, I can apply t just once to the sum of x1 and x2. This is a step where we use the properties of linear maps from 2 days ago. And that is in the image, because we just reproduce the sum as the one single image of some other vector in V. The third part of the subspace theorem, it's a scaling part. The same argument, I start off with the element in the image. I interpret what it means to be in the image. I interpret what it means to be in the image. That's the interpretation. That the vector can be recovered as the result of t on some x. Now if I start testing why the scaled vector, lambda y is in the image, all I need to do, that's the place where I borrow something from the properties of linear maps. All I need to say is that y lambda x equal to this, and that's exactly the vector in the image. And that's the end of it. The end of the proof that the image of a linear map is a true subspace. Any questions? Okay, so as I promised, now I'll show you why every span subspace, the second category of subspaces, you can think of it as an image, given that you choose a linear map properly. So here it is. That's my slide, which I call example of image of linear map. So look what I'm going to do. I'm going to take it's a very abstract example. In fact, it covers lots of examples at once. It covers all of the span subspaces at once. So I start off with the vector space. I'll fix a set of vectors within this vector space, m of them. See? I'll fix m vectors. I'll build now a linear map. Look what kind of map I'm building. I call it a T. It goes from the m tuples into this abstractly chosen V. V can be anything here, actually. This is the setting where my linear map works. Now, the formula for the linear map, look at this, what I say. If I take an m tuple with components xk, the action of my map on this m tuple is the action. I take the linear combination of this fixed set of vectors with the elements of this m tuple. It's a map. It takes m tuples into elements of my abstractly chosen vector space V. I need to convince you, of course, that this is a linear map. I will in a few moments. But before I do that, the immediate thing which is apparent right now from the construction is that the image of such map, it is something we used to call span subspace before. Because span, if you remember, it's the collection of all possible linear combinations of this fixed set of vectors. And my T does exactly this. It returns all possible linear combinations of these vectors. If you play around with the choice of these m tuples in a domain, you will come up with all possible linear combinations. So the image of this map is exactly the second category of subspaces we studied before, the span subspaces. And as soon as I prove that this T is a linear map, it will be an alternative independent proof that the span is a subspace. Because this time it will be like, because span is the image is a subspace, that's why span is a subspace. All right, but if you prove something, if you prove that something is a linear map, you have these two requirements to test, those which I called A and B, little a and little b, from 2 days ago. Here's A. I need to see that if I apply my T to a sum of two n tuples, remember, the vectors which you plug into this particular linear map, they are n tuples. You see the domain here is Fm. I need to show that if I take the T and apply it to the sum of two n tuples, that's what it will be if I apply T to a sum of two n tuples. And again, I use the same convention as before. If I use letter Y for the name, to name the n tuple, the components of that n tuple will use the same letter with indices. And the same about X. This is just this formula. Now we can use the properties of the vectors in the vector space. We can use the distributive law. We can rearrange the brackets like this. We collect all of the x's in one bracket, in one set of brackets, sorry, and we collect all of the y's in the other set of brackets, just a pure rearrangement of vectors in my expression. And now this bracket alone, it's exactly the T of X, and this bracket alone is exactly T of Y. And this requirement A of a linear map is verified. There is also requirement B for the scaling. Here it is. I apply my T to a scale vector, lambda x. X is an n tuple with components x1, x2, xn. So if I use this formula, that's what it will be. Again, if I rearrange the brackets differently, if I now put x1, a1 together, x2, a2 together, xm, am together, and the common factor lambda, I'll just pull it out. I'll have something like this, and that is exactly the lambda of T of X. That's the finish of the formal proof that this map I introduced is linear. And hence, the image of this linear map is subspace, and hence the span, which is exactly the image, is the subspace as well. It's a very powerful thing, I mean, in terms of arguing subspaces or not right now. I don't know if you manage to use them to the full extent when you do questions in the yellow book, but in principle you can. We just introduced totally different approach to the same categories of subspaces we knew before with the help of the linear maps, and this is a more powerful approach than the approach we had before. Any questions? Just there's a little note here which I just remembered. If you remember when we discussed with you spans, when we discussed with you span subspaces, I had a special lemma because spans you can introduce them in the context of any vector space, not necessarily n tuple vector space. However, in the context of the n-tuple vector space, spans take even simpler structure, some sort of metric structure. It's something which when we discussed this, I called it span in Fn lemma. I call it like this: span in Fn, wrong F. This is a term which I use to call this result. We had a special slide discussing it. So spans in general, they exist everywhere. I mean, you can construct them in a setting of any vector space, not necessarily n-tuple vector space. It might be a space of polynomials, of continuous functions, many other vector spaces. However, in n-tuple context, span, it takes a special structure. So if your V is Fn, then, yeah, that's right. Then in that case, we introduced also something which I call a column space of a matrix, where A was the matrix which consists of these vectors as columns. And in that case, span was exactly the column space of the matrix. If you just project those observations into the current linear map discussion, you will realize that this map T, which makes span as an image, in the context of n-tuple space, this map will be the matrix type linear map with this matrix A. So slowly things start coming together, and the whole picture becomes more or less transparent, I hope. All the subspaces, linear maps, matrices, column spaces. All of these things become just one single unity with just different names and different facets. Any questions? Okay, so I have one computational example. I mean, we just discussed, in fact, lots of examples today. We covered the whole categories of examples in one slides. But sometimes probably you're just expecting just very numerical example. I'll show you one numerical example. It's from the yellow book. It says, on my notes, it says question 25 from the yellow book, part C. But actually, before I do that, I will need to introduce two extra terms, which you have to remember. They are not like independent new terms. They are heavily linked to the first two we discussed today, the null space and the image of a linear map. The terms are rank and nullity of a map. These are simply, so again, the same context, vector spaces, map, linear map between these two linear spaces. So that's right, rank. The rank of a linear map, it's a number. It's an integer number. It's a positive integer number. Which is basically the dimension of the image of that linear map. We know that the image is the image is the subspace. It will have a basis. The number of elements in that basis, it's exactly the rank of a linear map. And nullity, similarly, it's the dimension of the null space. So these are two numbers. That's why I told you it's not like totally independent terms. They are linked to the first two, to the image and the null space. And now here's the computational example from its tutorial book, question 25, part C. In that question, you have very particular choice of a map. That's a map which takes quadruples into triples. It's a map which takes quadruples into triples. It's a matrix type map. So it's a map which is produced by multiplying a quadruple by a matrix. And the matrix in the question is this. Numerical matrix. You will soon realize that I told you this already 2 days ago, 99% of the linear maps in the yellow book, they all of the matrix type. So they are made up by some matrix multiplication. So the question goes to ask what's the rank and what's the nullity of this linear map. In the course of the solution, in the search for the rank and the nullity, of course, we will also identify the image and the null space of this linear map. So actually it covers everything numerically from today's discussion. So what do we do? The image, let's just look at the image first. The image of this linear map, which is as good as the column space of the matrix A, which is as good as the span of elements A1, A2, A3. That's exactly from what we discovered in the slide before. We know how to describe spans. We know how to find the number of linearly independent vectors within the given set. Remember, we are after the rank, which is a dimension, which is the number of linearly independent vectors within this set of 3. Why it's 3, by the way? It's supposed to be 4. Yeah, so this is A1 vector, this is A2, this is A3. I'm surprised it's somehow just supposed to be 4. My apologies. So it's supposed to be 4 vectors, not 3. So it's a span of 3 vectors. Yeah. So the image of my linear map is a span of columns of this matrix, A1, A2, A3, A4, right here. The rank, which is a dimension of the image, which is a dimensionless span, it will be the number of linearly independent elements within this 4. Numerically, we know how to do that. We need to do row echelon form reduction. I have free computation here. C is the reduction of my matrix A to the row echelon form. Here's the reduction of my matrix A to the row echelon form. By looking at this row echelon form, I see 3 pivots, which means that the first 3 are linearly independent. So in fact, if I drop this A4 from my span, nothing will change. Maybe that's the reason I had A3 originally. Because, yeah. So the last vector, the 4th vector, doesn't deliver anything new to the span. The first 3 linearly independent, and that's why the rank of my map T is 3. The dimension of a span, the number of linearly independent columns in my matrix A. Nullity. If I look for the nullity of my map T, I need to find the null space first. Null space is when my map takes the vector to 0 vector, which is, given that it's a matrix type map, it's a system of linear equations. It's a homogeneous system of linear equations. This system. So in fact, null space is just another name to something you knew very well even in the first semester. Because in the first semester you did it a lot. You solved homogeneous systems, you described the solutions in terms of the parameter. This is something we now have a beautiful name for, null space of a linear map. But computationally, it's something you know very well from the first semester. All I need to do, I need to analyze this row echelon form. I have one non-leading column here. So if I solve this homogeneous system, I need to parameterize the variable which is associated with this non-leading column. So here's my parameterization. It's x4, which I just gave a name, t, give a parameter name. And now I solve for the rest of the unknowns in terms of this t. For instance, if I solve for x3, I will solve from this line. And that's the solution for x3 in this line. Isn't it? It's just because x3 is just negative of x4. If I solve for x2, I need to use the second line in my row echelon form. This is the solution on my slide. 1/4 here because of this 4. 5 went into negative 5t, negative 3 went into negative 3t because we have extra negative here. If you do the arithmetic, it's negative double t. And finally, you solve for the last unknown, x1 from the first row, from this row, is a solution for x1. Again, 1/3 here because of this 3, and the rest is just the arithmetic of the rest of the components. and the result is double T. So if I combine now this solution into a vector form, that will be the description of a solution of this system in vector form, or if I use my new language, that will be description of the null space in the vector form. Here it is. It's my solution in the vector form. So I can say now that the null space is a span of one single vector, this vector. Because every element in the null space is of this structure. So if somebody asks me what the dimension of this null space, given that it's only spanned by one non-zero vector, the nullity of my linear map, which is a dimension of the null space, right here, is 1. This is a computational example. The thing which I can actually, with the help of this example, I can deliver one extra result, and that will be the final result I'll deliver, is that if you make this, if you add these two up, 3 and 1, which is 4, I hope everyone knows that, coincidentally, it's the dimension of the domain here, R4. Or in fact, it is not a coincidence actually, it's a deep result which bears the name. So if you add these two values, rank of T and nullity of T, it will be 4, which is exactly the dimension of the domain of my linear map. And this is something which holds all the time. This is something which bears the name rank and nullity theorem. And it says that the rank of any linear map plus the nullity of any linear map, it's always the dimension of the domain of underlying space. Of the underlying domain of the linear map. Some questions in the yellow book relies on your knowledge of this result. My computational example make a demonstration that this is true. It also, in fact, if you look deeper into this example, tells you why exactly this is true. So if you examine the proof of this rank and nullity result theorem, you will see that actually it follows almost the same computational steps I use in my example today, but we're not going to do that in class. If you're curious, you can check the yellow book. But the result itself, this time, it's something you need to remember. Any questions? We finished 5 minutes earlier, which is good. It means that I still have 5 minutes on your account, which I can claim back later if I'm late on something. Thank you very much. We're done today. Thank you.